Raj Singh, coordinator of Science Lecture Series. Today it is our immense pleasure to welcome Professor Gupta sir. And now I request Professor Venkatesh Singh to welcome our esteemed speaker and request him to present his talk. So, Professor Venkatesh Singh.
Hello everyone, this is Venkatesh of Central University of South Bihar, Gaya. Namaste and a very good morning. Today, I welcome all of you on behalf of the organizing team of this online science lecture series, which is organized by the Department of Physics, School of Physical and Chemical Sciences, Central University of South Bihar, Gaya. I would like to thank all the online participants for showing their interest and taking part in the season 2 first lecture of science lecture series. Today, we have the pleasure of having one of the world's most renowned astroparticle physicists, dynamic scientist, and my senior, Dr. Sunil Gupta ji from Tata Institute of Fundamental Research, Mumbai, and principal scientist of Cosmic Ray Laboratory, Ooty, Tamil Nadu, with us. I welcome you, sir. From the bottom of my heart, Dr. Sunil Gupta ji will speak on a very alarming issue which is directly associated with the life of living things on the face of planet Earth. The study of solar storm and their impact on Earth by Muons. A team of scientists led by Dr. Sunil Gupta ji using the GRAPES 3 telescope. For common audience, GRAPES stands for Gamma Ray Astronomy PEV energies, which detect and studies cosmic ray coming from space and anticipates and prepare for geomagnetic stars. Dr. Sunil ji is well-traveled and well-known figure in his area of research. He is elected members of various well-known national and international Academy of Sciences. This lecture will be a beautiful blend of basic experimental physics and its direct application, and as I believe, should not only attract use attention from the knowledge-loving physics students and young faculties, but also attract curious citizens and media personnel of our country, and may be the answer to many people who always question such mega science experiment. As I have always mentioned before each lecture, that our speakers are internationally renowned and real gems of their area. Therefore, they do not need detailed introduction. However, for curious participants, we have already uploaded his very short CV and the science lecture website and Facebook. Dear participants, colleagues, and friends, if you have any queries and questions related to the lecture, please write down in the chat box. At the end of the lecture, coordinator of this science lecture series, Dr. Vijay Raj ji will ask your question on your behalf. Once again, I welcome you, sir, and we are really grateful to you for accepting our request and delivering today's lecture, sharing time with us from your busy schedules. With these few words, I would like to request Dr. Sunil Gupta ji, please deliver his talk on study of solar storms and their impact on Earth by Muons. Dr. Sunil Gupta ji, please deliver your lecture.
Thank you, Professor Venkatesh Singh. My special thanks also to Professor Rathore, Vice Chancellor of Central University of South Bihar, Gaya. I am grateful to Professor Venkatesh Singh for not only inviting me, but always being also being a gracious host, giving a very kind introduction, and also being an old friend. So thank you very much, Professor Venkatesh Singh and other members of the organizing team. I'm really privileged to be able to interact with you on this occasion. But before I go on to the main topic, I want to put this in some context. So अगले कुछ मिनटों में मैं आपको एक चीज से अवगत कराना चाहूंगा. हम सभी कोविड-19 के पेंडेमिक से प्रभावित हुए हैं और यही कारण है कि ये लेक्चर मैं आपके सामने खड़े होकर देने की जगह ऑनलाइन दे रहा हूं. और आप जान सकते हैं कि ये इसीलिए संभव है क्योंकि इंटरनेट पे हम निर्भर करते हैं और आज की तारीख में इंटरनेट पे हमारी जो डिपेंडेंस है वो पहले से कहीं अधिक बढ़ गई है. और यही एक ऐसा टूल समझ लीजिए जो है जो कि हमें कोरोना वायरस से सुरक्षित रखे हुआ है और हमारा जीवन आसान कर रहा है. तो इस अवस्था में आप कल्पना करें कि अगर हमें इंटरनेट के और बिजली के बिना रहना हो तो कितनी बड़ी समस्या खड़ी हो जाएगी. और यही सब कुछ करने की क्षमता रखते हैं सोलर स्टॉर्म, जिनके विषय में हम लोग आज चर्चा करेंगे. अब आप दूसरी एक समस्या भी देख रहे हैं कि हमारा एक पड़ोसी देश भारत की सीमा पे बहुत सारी समस्याएं खड़ी कर रहा है. आप सब उससे अवगत हैं. न केवल हमारे पड़ोस में पर दुनिया में भी काफी समस्याएं खड़ा कर रहा है और कुछ समस्याएं उनके जो 5G नेटवर्क बनाने से भी संबंधित रही हैं. और इसी विषय को लेकर लगभग 1 वर्ष पूर्व बीबीसी की एक टीम हमारी लैब में ऊटी आई थी और उन्होंने हम लोगों से चर्चा करी थी और उसके आधार पर एक वीडियो बनाया था जो कि काफी पॉपुलर हुआ है. जैसा कि आप अंदाज लगा सकते हैं, उसका लिंक मैंने यहाँ नीचे दे रखा है. हमारे देश के लगभग 16 देशवासी इसको देख चुके हैं और ये तमिल और तेलुगु भाषाओं में भी उपलब्ध है. तो मैं आपके साथ ये वीडियो दिखाना चाहूंगा कि जो भी हम लोग कर रहे हैं उसका और भी जीवन की रोजमर्रा की चीजों से संबंध है. तो चलिए आगे बढ़ते हैं. तो ये आप जो दृश्य देख रहे हैं, दिस इज अ व्यू ऑफ ग्रेप्स 3 एक्सपेरिमेंट एंड व्हाट द बीबीसी वीडियो डिस्क्राइब्ड एज यूएफओस आर एक्चुअली यूएफओ. हेलो, हाँ जी.
Yes, sir. Yes, sir.
You can hear, right? Okay. So
Yes, sir.
what the BBC video described as UFOs are not UFOs. They are just our detectors. Each of these cone-shaped structures that you see are 1 meter area plastic scintillator detector. There are 400 of them. They are distributed over an area of more than 25,000 square meters in the beautiful hills of Ooty. And what you see on the left side, these white halls are part of the Muons telescope with a total area of 560 meters square. Now, all this work cannot be done by a few people. In fact, we have a fairly large collaboration of 15 institutions that are listed here from India and Japan. And the names of scientists are mentioned down here. And in fact, this is probably the largest India-Japan scientific collaboration going back almost 30 years that is working at Ooty. Now, I mentioned plastic scintillator and proportional counters. And except for the bus you see here, everything else is made by the members of this laboratory. For example, the plastic scintillators that are used are manufactured in our lab. The proportional counters are made in our lab. There are thousands of them. Now, all these detectors produce signals, and those signals have to be processed by electronics, which is fast, with nanosecond response time. And that also has been developed and fabricated in the lab. And when all these detectors produce signals which are processed by signal processing electronics, you generate a lot of information that has to be recorded by data acquisition systems, which are also designed and developed and fabricated in the lab, as well as maintained. And finally, all this information has to be recorded and analyzed to produce science For that, we need large-scale computing power, and that also computers are assembled from basic components by members of our collaboration, some of whom are also watching this lecture today. So as a result, we do not depend on outside agencies to do our maintenance or supply us components. So we do it everything ourselves. And in that sense, I can say that we are entirely Atmanirbhar. Okay, since we are discussing this lecture on Google Meet, I thought we'll share a Google view of the laboratory site. And you can see these white dots. These are 1 meter square scintillator detectors, which can be clearly seen, deployed on a hexagonal pattern. And then you see these 4 squares, black squares. These are the top roof of the 4 Muon telescope supermodules. And then this is the new Muon telescope, which is under construction, which will be superior to the existing one. Let's move on. Now, if you look at the map of our country on the left side, I am stationed at moment in Mumbai on the west coast, and most of you are in Bihar, and of course from different parts of the country as well. And Ooty is about 1,000 kilometers south and slightly east of Mumbai at an altitude of 2,200 meters. The plan of my talk is as follows. The first question which naturally arises, why study cosmic rays? Because cosmic rays are the ones which produce muons. So that is an important question to ask. The second point deals with what benefits it will bring to the society. Some of the glimpse of that benefits you saw in the video. Of course, I will describe the grade 3 experiment in some detail. And then finally, I'll come to the main topic of today's lecture, and that is study of solar storms. There's another very important area that can be studied by grade 3 Muon telescope, and that is thunderstorms. As you all are aware, that thunderstorms are also one of the leading causes of death in our country. In fact, unfortunately, a little over a month back, we had torrential rains and massive thunderstorms in Bihar and UP, and hundreds of our countrymen lost their lives. So this is something also which is very relevant, but today I don't have time to go into discussion of thunderstorms, so I'll only stop at solar storms. Now, the graph you see on the bottom right side, basically it shows on the x-axis the energy of cosmic rays. And you may not be able to read it, so I will read it for your benefit. The lowest energy cosmic rays start at 10 raised to 10 electron volts. And it goes up all the way up to 10 raised to 20 electron volt. So these are the highest energy particles produced in the universe. Now, to get a sense of what 10 raised to 10 electron volt means, for example, when we deal with, when we look at each other, like we are watching this lecture, we basically rely on photons which are produced by, for example, on your screen, which makes an image in your retina, and your brain interprets it as the screen, okay? And then you can read everything. But that communication happens through photons, which have energies between 2 and 3 electron volt. That's all the energy that is there, invisible photons. If you go up by a factor of 1,000, you get X-rays, which are kilo electron volt. If you go up by another factor of 1,000, you get million electron volt. Those are gamma rays, which are produced in nuclear decays and various other nuclear reactions, the kind which my colleague Professor Venkatesh Singh studies in great deal of detail. So these are the highest energy naturally occurring radiation on Earth. But the lowest energy cosmic rays are 10,000 times higher than this energy and go up all the way up to 10 raised to 20. That is 10 raised to 14 times higher energies. So the question arises, how particles are accelerated to such high energies, how they propagate in the universe to arrive, to reach us, and what are these cosmic rays? What is their composition? These are important questions. So let's start looking at some of these questions. Well, for lack of time, I will not describe in detail what cosmic ray composition is, except to tell you that almost 90% of them are protons, which are basically nuclei of hydrogen atom. There is no electron present, it's just proton. Now, when this proton enters our atmosphere, it interacts with, let us say, another proton or neutron in the oxygen or nitrogen nuclei which are present in the atmosphere. And in that interaction, it produces secondary particles known as pions. These are of two varieties, charged pions and neutral pions. By converting energy into mass of new particles, the famous equation E equal to mc square, the charged pions decay to give you muons and neutral pions decay to give gamma rays. So we'll not worry about neutral pions. We'll focus, because our main interest is in muons. These muons are very special particles. They are actually known as the penetrating cosmic rays or penetrating component of cosmic rays. And these muons acquire their special properties because of the fact that they are 200 times more massive than electron. As a result of that, they lose their energy only by ionization at a constant rate. So if you have a muon of a given energy, you can actually calculate how much it will travel in matter. In fact, they can penetrate buildings, they can penetrate deep underground or deep under the ocean as well. And therefore, they are actually far more effective than X-rays, which we normally use for example, diagnostic purposes. If somebody has an accident, they are subjected to an X-ray exposure, and from that X-ray image, doctor can make out whether that individual has suffered any fracture or dislocation, because X-rays penetrate the flesh but not the bones. So you get the image of bones. But muons can give you image of an entire mountain or an entire underground structure without actually you having to go inside. And I'm not joking. In fact, about 3 years back, some cosmic ray scientists examined the Great Pyramids of Giza in Egypt and found one of them contained a large cavity which otherwise nobody would have found other than by dismantling the pyramid, which of course you cannot do. And this result was published in a paper in Nature, and I have given reference here. So you see, muons are very fascinating probes of nature. Before moving on, I want to draw your attention to one more fact, and that is our atmosphere. Of course, we all know what our atmosphere is. It's almost 80% nitrogen and about 20% oxygen, with a little mixture of other gases, greenhouse gases and so on and so forth. But the pressure of atmosphere at sea level, for example, at Mumbai, where I am right now, is about 76 centimeters of mercury column. Now, if you multiply the height of mercury column by its density, which is 13.6 grams per cubic centimeter, you get a total mass of 1034 grams per square centimeter. That is the mass of mercury column that is supported by atmospheric pressure, which means atmospheric mass over a square centimeter of area is also 1034 grams from sea level all the way to the top. So let's round it off to 1000 grams. And so atmosphere is equivalent to a kilogram of matter. So if you were to replace atmosphere by, let's say, a plate of stainless steel, you will need a stainless steel plate which is 125 centimeters thick. So you see, atmosphere is a huge absorber. Only thing we don't notice it because it's transparent and we can walk through it, we can see through it, etc.
Excuse me, sir. We are not able to see your slide.
Oh, I think maybe because
someone.
Okay, someone called Sakil Ahmad started sharing his slide. So Sunil's slide was not, it suddenly moved away, but there is no slide there. So whoever is Sakil Ahmad, please stop sharing and then let Sunil share it.
Thank you, sir. Thank you.
Okay, is it visible now?
Not yet, Sunil. This is Brajesh Chaudhary.
Oh, okay, Brajesh. Okay, I'm sharing it, but okay, so maybe I'll have to go again and no, it says share. I'm sharing it.
No, it's not coming on full screen, Sunil. Where you are presenting it shows, but it is not coming on the full screen of anyone watching.
Is it now full screen?
Not yet. Not yet.
Is it partial screen? My screen is visible?
Not yet,
sir, I think one time you can withdraw and again share.
Okay, okay, I will do that. I will stop sharing and I will share again.
So I request to all participants who are attending, please don't do anything in this one. Otherwise, it will be slightly disturbed. So please just listen, and if you have any questions, so you can type your question in chat box. Later we can ask.
Is it visible now?
Yes, sir. Yes, sir.
Okay. Okay.
Now you okay, sir?
Perfect, sir.
Okay. So as I was saying, that we can think of atmosphere as a slab of matter of thickness 1000 grams per square centimeters, and as you come down the atmosphere, the number of cosmic rays decrease. So you would like to be at a higher elevation so that you can detect more of them. So Ooty is at a height of altitude of 2.2 kilometers above sea level, where the atmospheric depth is 800 grams per centimeter square. And that is the reason we chose to work there. Ideally, we should be still higher, but then, it's much harder to work at higher elevations than relatively lower elevations. And that is why we, as a compromise, we chose to work at Ooty. Of course, there are other advantages, which I will describe. Now, all these particles, unfortunately, we cannot see with our eyes, because our eyes are not the ideal sensor for detecting charged particles or gamma rays. We need special sensors, and those sensors are known as detectors, which you all know. And they can be broadly classified into two categories: scintillator type of detectors and gas-filled detectors. So I will describe each one of those, which we use at Ooty. And what you see on this picture, these blue sheets of plastic, is actually a plastic scintillator, which we developed in-house in Ooty using raw materials. And what you see is a sheet of plastic which is 1 meter long. And in this case, in this example, if you can see the arrow that I'm moving, you can see through the entire 1 meter depth, which tells you that it is a highly transparent medium. And it has very low attenuation. Now, scintillator is a very fast sensor. It produces a flash of light whenever a charged particle goes through in about a nanosecond. So you actually can measure speed of light using these plastic scintillators, and these have been developed. And they're used at a number of institutions in India and abroad. Some of them I have listed down there. And these are the scintillators we are using in our those detectors, plastic scintillator in the detectors I showed. The second example of a gas-filled detector is proportional counter. And here I would like to first share with you some pictures of fabrication of these proportional counters. These are, in our case, these are square tubes with a cross section of 10 centimeter by 10 centimeter, and they're 6 meters long. So they're long square tubes. And here my colleagues in the first picture on top left are cutting it to appropriate size. And then another team of colleagues are basically cleaning it to remove any rust or other impurities that might be sticking to the surface, especially the inside surface. And then after that, after the tube has been cleaned, two of my colleagues are welding end plates to make it a complete sealed system, except for holes in the center of those end plates at both ends, where we put a hermetic seal which insulates a central wire of 0.1 millimeter diameter that is threaded through the hermetic seal. So the central wire acts as anode and the outer body acts as cathode. So after we have put these wire and sealed it, then my colleague here is testing if there is any leakage by evacuating these tubes and observing if the vacuum is maintained. After it has been certified, then of course it's properly painted, etc. And here a colleague of mine is testing them in a stack of 128 proportional counter by just studying the muons passing through them. So how do they operate? Basically, as I said, we apply a potential of about 3000 volts across anode and cathode, and it is filled with a special gas mixture. So when a charged muon or any charged particle goes through, it ionizes the gas, producing electron-ion pairs, and the electrons are attracted towards central wire. They are rapidly accelerated because of increasing electric field, and they knock out more electrons. As a result, you have multiplication process, and from few electrons, you can get tens of thousands of electrons. And that can be then picked up very sensitive by sensitive electronics, which also is developed in-house, and the signals can be amplified and recorded. And what you see on the panel on the right side at bottom is the distribution of signals from this proportional counter. First, you see a peak, which is labeled Fe for iron, and second is labeled zinc. And this is when, this tube is made up of iron and it is coated with zinc. So when an electron in the innermost shell of iron nucleus, iron atom, is knocked out by a muon, a electron from a higher orbital jumps down and produces a 6.4 keV photon by what is known as K alpha emission, and that causes the first peak, and the corresponding peak in the case of zinc is at 8.6 keV. So we have two energy measurements, iron and zinc, and from that we can calculate the energy of muon peak, which is about 20 keV, and that is exactly what we expect. So that tells you that it is capable of detecting muons. Now we had manufactured nearly 4,000 of these tubes, 3,800 to be more precise, for the requirement of the new muon telescope that we are building. And in fact, BBC ran a very detailed article on it because they were very fascinated by the fact that we use these old tubes, recycled them, and turned them into sealed proportional counters, which can then be used for several decades without having to service them. Now, what do we do with all these tubes? We lay them out in form of platforms. You can see each of these platforms is similar to what I'm going to show you with the existing muon telescope, but a newer and better design. So we have a layer of proportional counters, then a layer of concrete, then another layer of proportional counter. So we make a sandwich of proportional counters and concrete, and a total of 4 layers of proportional counters are used. And then you can see here, we are making some passage so that people can walk around it. This was in May 2018, and about a year later, the roof has been put. Of course, right now the work had to be stopped because of pandemic. Once it is over, we'll complete this muon telescope, and this will be then the most sensitive muon telescope operating anywhere. And this is the existing muon telescope. Here, all 16 modules are in under a single roof. Here, they are divided into 4 super modules of 4 modules each. So let's let's see what we do with all this hardware. So as I mentioned, we have nearly 400 plastic scintillator detectors, each of 1 meter square area, and we have 560 meter square area muon telescope, which will soon get doubled when we complete the construction of new muon telescope. So what is the purpose of all this? See, the basic objective is to do high precision measurement. In science, as all of you know, if you have an instrument which has the same sensitivity as others, then you'll make the same measurement as what others have done, which means you will not find anything new. We can only confirm what others have found. So the challenge here for us was to design something which is better than what exists anywhere else, so that we can do something new. And that is why the emphasis here is on high precision measurements. And of course, this over the year, this experiment has produced many PhDs, both from India and Japan, and some of the names are listed here. Okay, so let me now come to the objective of this activity. To tell you the truth, when we started studying a solar storm was not one of them. It somehow happened by sheer accident. But then in science, many things happen by accident, as you all know. Most of the discoveries are not planned, but happen unexpectedly. So the objective here is to study universe at high energies, because at high energies, we would like to know how particles are accelerated, okay, to such high energies, how they propagate in the universe, and what extreme conditions that exist that allow particles to reach such high energies. And these are important questions. To address some of these questions, we basically pursue 4 broad areas. We study acceleration of particles in atmospheric electric field, which are produced during thunderstorms, where particles can reach energies as high as a giga-electron volt. So these are not tiny accelerators. The scale or the size of this accelerator are the size of a thunderstorm, which is as large as 10 kilometers in diameter. Then, of course, we study the phenomena occurring on the surface of the sun, known as solar flares, coronal mass ejections, etc., where energies are almost 10 times higher, and the scale is the scale of the size of the sun to all the way to the size of the orbit of Earth around the sun. And third topic of interest is to study galactic cosmic rays, where our accelerator is the galaxy itself, and the energies are nearly 1 million times higher than in thunderstorms, and the scale of the accelerator is the size of our Milky Way galaxy itself. And final topic of interest is to study multi-TeV diffuse gamma rays, which are produced as a debris of through the propagation of highest energy particles in the universe. And here the scale is out to a distance of about 100 million light years. Now, 100 million light years seems like a very long distance, but compared to the size of the universe, it is really very, very tiny. So these are the areas that we are pursuing. And of course, I don't have time to get into all of them. So let me come back to the Muon telescope and its view. So this, you see a close-up of the 4 super modules of Muon telescope, and this is the inside view. And what you see is that there is a layer of concrete blocks, which is 6 meter by 6 meter in area, in which we have put a layer of proportional counters. And if you put 60 of them, they will cover a distance of 6 meters, and you will cover an area of 6 meter by 6 meter. And then you have, in reality, we have put only 58. And then you have another layer of concrete and a second layer of proportional counter, which is perpendicular to the original direction, and a third layer of concrete blocks, and another layer of proportional counter. Now, in this case, it's parallel to the first layer, and same thing is done, and a fourth layer of proportional counter. So when a muon passes through all of them, for example, let's say it passed through this particular counter. Now I know its location within 10 centimeter, because that is the size of my proportional counter, the location in this direction. Okay, but I don't know what its location is in the perpendicular direction, but that I can get from the bottom layer. So you see, if this gives me a y measurement, this gives me an x measurement. So I have one x, one y, second x, and second y measurement. Since I have 2x and 2y measurement, I can define 2 points which I can join, and I can get the direction of muons, and that is what a telescope does. And now this Muon telescope basically maps the sky into 169 pixels. Now you may wonder, even your mobile camera has millions of pixels, so this is not a great telescope. But remember, we are not dealing with photons, we are dealing with muons, which are impossible to, almost impossible to bend and focus, etc., etc. So a 169 pixel camera is a great improvement in the sense that, especially when you compare with other competing instruments which are only 1 or 4 pixels. So this is a much, much better device. And now let's see what we can do with this device.
Sunil?
Yeah.
So now, since you have used these old stuff into your proportional counter, what is the efficiency of the 4-hit track? So let's say that a muon is coming, which is going through all the 4 layers.
It's about 96%.
Okay, thank you. Thank you.
Okay, so before I talk about that, let's look back in history. Let's go back 160 years. On 28th of August, 1859, 2 bright regions, A and B, which I have shown here in red, they look like 2 red chilies. 2 bright regions, A and B, appeared in a sunspot that were observed by a British astronomer by the name of Carrington. And on 1st September 1859, the biggest solar storm in recorded history reached the Earth at a speed of 2,400 kilometers per second. And normally you see auroras near North Pole or South Pole. So those are known as aurora borealis in Northern Hemisphere, in Southern Hemisphere, aurora australis. But in this case, the aurora were seen at low latitudes, somewhat close to equator as well, which was just incredible. We don't expect to see aurora, for example, from India. And then it caused huge disturbance in Earth's magnetic field, and that is measured by index. It was 1600 nanotesla. Typically, this index is about 10 nanotesla. So it was 2 orders of magnitude, or 100 times larger than what normally you see. In those days, there were no electrical power being used. It was still another 20 years before Edison will invent his light bulb. The only technological infrastructure that existed was telegraph lines, which were operating in Europe and USA, and they ceased to function. They actually caused a lot of problems. So this was the power of this solar storm, which caused serious disruption. Okay, so now you come back to closer to now. In 2016, one of the very well-known science journals, Science, had published an interesting article which said, here is how the world could end and what we can do about it, and lists 3 major threats. Threat 1, solar storms. Threat 2, cosmic collision. And threat 3, supervolcanoes. Now I'll go in the reverse order. Let's look at supervolcanoes. Now supervolcanoes are also volcanoes, but they are much more powerful, and they happen once in about 100,000 years or 1 lakh years or so. The last one happened in Indonesia about 74,000 years ago. And it actually results in so much ash being thrown into upper atmosphere that it blanks out sun for years together and kills most of the life forms on Earth. So that is something that can happen, and there is very little we can do about it to stop it. Second threat is cosmic collisions. Now, this is where an asteroid or a comet can crash onto Earth, and it is not something that has never happened. We know something similar might have happened 65 million years ago, which wiped out all the dinosaurs and which allowed humans to evolve on Earth possibly. There is nothing we can do about that either. And then there is the threat one, which is solar storms. Now, solar storms is something that does not harm human beings directly, but their effects can be spectacular. By funneling charged particles into Earth's magnetic field, they can trigger geomagnetic storms and ignite auroral displays. But these have another dark side, these storms. They can induce dangerous electrical current in long-distance power lines. Though these currents last only a few minutes, but they can destroy the electrical grids by destroying high-voltage transformers. Okay. Now, you see, in our country, we transmit high voltage power at 440 kilovolt. And you can see these high voltage transmission lines, which are very tall poles on which these wires are mounted, which carry this huge voltage. But the only insulator that they have, real insulator, is the air between them, because air is a good insulator. But during a solar storm, the air gets ionized and becomes conducting. So it short circuits the voltage, and as a result, the transformer will try to supply more current and will overheat and burn itself out. And high voltage transformer is something which takes years to build and install, so it's not something you can replace overnight. So they are a serious cause of disruption. So at that time, a few months after that article, the President of the United States issued an interesting executive order. But before I come to that, I want to explain to you some of the terminology which is used in this field, which can look quite confusing. So, as you saw, Carrington saw some activity on the surface of the sun, which looks like a fire. So it is called solar flare. So these are basically high, temperature, high energy plasma that is flaring up from the surface of the sun. It is known as solar flare. But sometimes it is so powerful that it throws out large amount of plasma into space carrying magnetic field. And plasma means it's mostly protons, electrons, and so on and so forth. So this is known as coronal mass ejection. So it's the same phenomena which leads to large volumes being thrown into space is known as coronal mass ejection. And then if it has enough energy, it travels through the interplanetary space towards Earth. And there it is known as solar storm. And eventually it reaches Earth and disturbs magnetic field of Earth and causes a lot of disruption of communication, etc. And that is known as geomagnetic storm. And the study of this entire field is known as space weather. So these terms can be sometimes are used interchangeably, so you have to be aware of it. So President Obama's executive order stated, coordinating efforts to prepare the nation for space weather events. By the authority vested in me as president by the Constitution and the laws of the United States of America, and to prepare the nation for space weather events, it is hereby ordered as follows. It's an order. Space weather events in the form of solar flares, solar energetic particles, and geomagnetic disturbances occur regularly, some with measurable effects on critical infrastructure systems and technologies such as GPS, satellite operations, communication, aviation, electrical grid, etc. Okay, and extreme space weather events, that is extreme solar storms, that could significantly degrade critical infrastructure, could disable large portions of electrical power grid, resulting in cascading failures that would affect key services such as water supply, healthcare, and transportation. Space weather has the potential to simultaneously affect and disrupt health and safety across entire continents. Successfully preparing for space weather events is an all of nation endeavor that requires partnerships across government, emergency managers, academia, the media, insurance industry, etc., etc. This is a 4-page long order. I just picked up one paragraph. So you see, they took it very seriously and they have started preparing. Now, what is important here is to recognize that this is something which is not just speculation. This is something that can happen. Doesn't happen frequently, but has happened in the past and will definitely happen in future in an unpredictable manner. Okay, so before I talk about grapes 3, I want to share with you the sensitivity of this instrument. I kept talking about high precision, but you should not take my word for it. I should convince you by showing you some data. So the top graph shows the temperature of the upper atmosphere above Ooty, where muons are produced. Now, the upper atmospheric temperature does not change day to day. Okay, day and night variation is almost negligible. But over a year, in summer, the upper atmosphere gets heated up. In winter, it cools down. By how much? It cools down by 1 degree Celsius or Kelvin in winter, and it heats up by, so variation is plus minus 1 degree. And you can see, we can clearly see the variation in muon intensity anti-correlated with temperature. So as the temperature increases, muon intensity decreases. And we can fit and get a coefficient of muon intensity dependence on temperature. And from this fit, we can estimate how precisely we can measure the variation in upper atmospheric temperature, and that is 0.06 degrees, 1/16th of a degree. So that is the sensitivity of grapes 3 instrument as a thermometer of our atmosphere. Below, I show you the variation in atmospheric pressure versus the change in muon intensity. Again, the same thing. Increase in pressure causes atmospheric mass to increase, and the muons get absorbed at a larger rate, and you get a drop in muon intensity. And again, from this bit, we can estimate the sensitivity of muon telescope to changes in atmospheric pressure. Now you see, as I'm sitting in front of you, or all of you, if you ask the question, the atmospheric pressure near your chin is higher than atmospheric pressure at the top of your head, because your top of your head is in higher elevation. Normally, we don't worry about such small pressure changes, but this muon instrument is so sensitive that it can detect changes in atmospheric pressure caused by a column height of 20 centimeters. That's how sensitive it is. So let me summarize. Grapes 3 is a unique instrument. It is incredibly sensitive. It can act as a barometer, indirect one though, of atmospheric pressure. As I said, it can measure pressure changes as small as those caused by a 20 centimeter height air column, which is 2,000 times smaller than the blood pressure change it happens in our body. It's a very sensitive thermometer. What I did not explain to you for lack of time is also it is a very sensitive magnetometer of interplanetary magnetic field. You see, the space outside the Earth's atmosphere is not vacuum. It contains plasma. It contains magnetic field. So changes in that magnetic field as small as 0.1 nanotesla can be detected by this muon telescope, which is million times smaller than the magnetic field of Earth. Now, typical magnetic field in interplanetary space is about 5 nanotesla. So it can measure changes as small as 0.1 nanotesla. It's also a very powerful voltmeter. It can measure voltages in thunderstorm of gigavolt and higher. It also is a very sensitive current ammeter. It can measure muon current as small as a femtoampere with a precision of attoampere. Now, you all know attoampere is very small. It's just flow of 6 electrons per second. So now that I have shown you all these things, so what do we do with this? Well, we observe muons. Now, this is in this graph, you can see I'm showing you the variation in muon intensity over a period of 20 days. The first thing you notice is that muon intensity shows a cyclical variation with a period of about 1 day, but it is not sinusoidal. Its amplitude varies. And the reason we see this variation is because when Earth points in the direction of sun, it is directly in the line of plasma coming from the sun, which carries magnetic field and does not allow cosmic rays to reach us easily. As a result, the muon intensity drops, okay? You get a minimum intensity. And when it points away from the sun, then the muon intensity is higher. And since the amount of plasma reaching the Earth varies day to day, because this is known as solar wind, and solar wind is not stable, we see this variation. Normally, you have to launch a satellite in space to measure this variation. In fact, satellites are used precisely for such studies, so-called space weather studies. But you can see this instrument is so powerful, it tells you sitting on ground what is happening in space, interplanetary space. So we see this cyclical variation, nothing surprising. But please note, this variation is 1%, but we can see structures which are very, very tiny at the level of 0.01, 0.02%, which are real variations, which no instrument in space can record. The sensitivity which this one can do. Okay. And then you see after some time on day 172, we don't count days by day and month, we count day of the year. So our clock runs from day 1 to day 365, and then it resets to next year. You see, then suddenly the intensity dropped by almost 2.5%, and then gradually recovered. This is also not surprising. This phenomena is known for 80 years. It was discovered by an American physicist by name of Forbush, and it is known as Forbush decrease. But what is remarkable is you see the sharp spike when this intensity was reducing. The intensity was decreasing and there was a sharp increase, and then it went down again. And this was something new. And this was something which was immediately spotted by my young colleagues in Ooty who were observing that this has happened. This happened at midnight. And it was promptly reported in one of our meetings. And but we didn't have a clue what it was. Okay. So now let me digress a little bit and tell you how do people study space weather. Now, if you want to study space weather, you have to give advance warning on Earth. For that, you have to have a probe which is not on Earth, because by the time the solar storm reaches Earth, it is already too late. So what people have done, various space agencies like NASA and European Space Agency have done, they place satellites at a point called Lagrange point 1 or L1, which is at a distance of 1.5 million kilometers from Earth in the direction of Sun, where the gravity of Earth and Sun balances out. As a result, if you leave an object there, it will co-rotate along with the Earth around the Sun. So any solar storm propagating towards Earth would first reach L1, where the satellite will measure its properties, relay it by radio waves to Earth, and to travel a distance of 1.5 million kilometers, the radio signal will take 5 seconds. So 5 seconds later, you will get a warning. But the solar storm traveling at the speed of few hundred kilometers or 1,000 kilometers will take of the order of half an hour. So you have half an hour warning. That is the purpose. And in fact, ISRO is planning to launch a similar satellite called Aditya L1, possibly next year or year after that, to do exactly that. So since we cannot do all these things sitting at Earth because we don't have access to space, so we had to wait until the information became available. And what you see on the top graph is the speed of this plasma of solar storm. And you see it was showing jumps. Initially, it jumped from 300 to 350 kilometers. Then it went above 400. And at this point, it jumped suddenly by almost 300 kilometers to 700 kilometers. And if you see the second panel, which is shown in green, it shows the magnetic field, which was around 10 nanotesla. And then at this point, it jumped to more than 40 nanotesla. But what is even more remarkable is the component of this magnetic field. You see, magnetic field is vector, so you have X, Y, and Z component, and Z component is defined as the direction in which Earth's magnetic field lies. So this magnetic component went south, almost 40 nanotesla. So all of the IMF, interplanetary magnetic field, was southward directed, opposite to Earth's magnetic field. And this is exactly when we saw the burst in muon intensity. They look so similar. Now, this happened on 22nd June 2015. The satellite information tells us that it ejected 10 raised to 10 tons of high velocity plasma into space during this eruption. It carried total kinetic energy of about 10 raised to 33 Earths, which is comparable to solar power. The initial speed of the storm was 1400 kilometers per second. And by the time it reached Earth, it slowed down to 700 kilometers per second. Just to give you a sense of, at 700 kilometers per second, I can reach from here to Gaya in 2 seconds, right? And come back in another 2 seconds. Unfortunately, we cannot travel so fast, but plasma does. Now that we see the similarity between them, so what do we do next as scientists? Well, we reverse the polarity of magnetic field and look at that. And you see, what do you see? You see the muon intensity shown in blue, and the red dotted curve shows the magnetic field measured at L1. Remember, blue is measured on Earth and red is measured in space 1.5 million kilometers away. And you look at the shapes, they are 98% identical. Now, this is something remarkable, that two phenomena, if they have nothing to do with each other, there is no way they could look identical unless one of them is responsible for the other one. And of course, just for fun, we have put a number called 54 sigma. That is the significance of this effect. Okay, and this happened at midnight of 22nd June. Okay, now since we have some particle physicists in audience also, I could see that. So typically in science, if you have a 5 sigma measurement, you claim a discovery, right? So when Higgs boson was discovered, they had 2 measurements by Atlas and CMS experiments of 5 sigma each. And when gravitational waves were discovered a few years later, they had 2 measurements of 5 sigma each. But here we have 54 sigma measurement, but it was done by 16 independent telescopes. Each one of them is 13 sigma. So there is no way that this could have been produced by any kind of accident. It has to be due to the phenomena of solar storm. So this is what we saw. Since I mentioned that we have a telescope, so we can look in different directions. Now you see in the center, you see the view of the muon, we called it a burst, muon burst in vertical direction. And you see it north, south, east, west, northwest, northeast, southeast, and southwest. So we have 9 directions. But what is interesting is the burst happened in all directions simultaneously. Now, let's again digress. If I ask you the question, where do we see moon? We see moon, for example, first in east, then gradually it rises, it reaches almost, vertical, or let's say approaches zenith, the highest elevation, and then it sets in the west. You don't see, but here it is like seeing moon at the same, at the same time in all directions. That can only happen if the moon was very close to us. Then of course you will see it from a location in all directions, right? So we knew from this phenomena, from simultaneous occurrence, that this is a phenomena which happened in close proximity of Earth, and it was not far away. So this is first clue. The second clue I already told you, we suspected it is due to magnetic field. So my colleagues carried out a very detailed simulation or calculation where they assumed, so what is our hypothesis? The primary hypothesis is Earth has a magnetic field. What that magnetic field does, it bends the trajectory of incoming cosmic rays such that the low energy cosmic rays cannot even reach us. So for example, if you look in west direction, you have to have a minimum energy of proton of 15 GeV for it to reach Earth at Ooty from vertical direction. But in vertical direction, it needs still higher energy of 17.3 giga electron volt. And east, it rises to 22 giga electron volt, etc., etc. So you see, particles of energy lower than that cannot even reach Earth. But imagine if you have plasma coming from the sun carrying magnetic field, which is oppositely directed, then of course Earth's magnetic field will become weaker, and particles which otherwise would have been sent back into space now can reach the Earth. Okay, and that is the explanation we gave, that basically the Earth's magnetic field became weaker, so the intensity of muons increased because more cosmic rays could reach Earth. And that also explains why the shape of the muon burst looks exactly identical to the shape of the magnetic field measured in space 1.5 million kilometers away. Okay, so far so good, but of course nobody will believe that unless you do detailed simulation. We did detailed simulation, and for each direction, and you saw the simulation results are shown in red dotted lines, and you can see they almost, not exactly, but very closely reproduce what we observed. So this was fine, but there was a problem. The problem was the amplitude of the effect was almost 20 times smaller than what we are actually observing. So this was a mystery. So we carried out another calculation to see how, if, for example, 40 nanotesla somehow increased to 80 or 100 or 200 or 300, what would happen? And what you see on the graph on the right, it showed that the amplitude of the muon intensity scales exactly as the strength of the magnetic field. So if we enhance the magnetic field, the effect gets enhanced. So if we use a common factor of 17, it fits the data very well. So we claim that the magnetic field got enhanced from 40 nanotesla to 680 nanotesla, and that could then explain. Okay, and there was one more mystery which I will address later on. So we could explain very well. The other mystery was, why did we see in the middle of the night this effect, right? Because as I said, anything related to sun should be seen during daytime. In India, it was midnight. On the North and South American continent, it was daytime. So there we did the study of those cosmic rays which entered the Earth as a result of weakening of Earth's magnetic field, and found that those cosmic rays were bent by Earth's magnetic field by almost 180 degrees. So you see this on the left, you see a polar view of Earth. This is the North Pole. Cosmic rays are coming. These are for 9 different directions. They are coming from the west. They're bent by the magnetic field and they reach Ooty or India. And if this is the equatorial view, you can clearly see the bending of particles, and that is why we saw it at night. So we could explain all these things. And this, of course, we published, this result we published, which attracted considerable amount of attention. And much of what has been, what is written here in abstract, I have already said, except I want to mention one last point, and that is this phenomena, because we said it is weakening of Earth's magnetic field. Sorry. It indicates a transient weakening of Earth's magnetic shield and may hold clues for better understanding of future superstorms that could cripple modern technological infrastructure on Earth and endanger the lives of astronauts in space. So this is something which we stated, and that actually became, I think it created a huge amount of excitement, and there was worldwide coverage in large number of countries, and my younger colleagues who were keeping track of all this used to list all the names of countries, and finally it became too long. So what we did was they basically painted the map of the world in the color of our flag. Wherever a report appeared, they labeled it either as saffron, white, or green, and the countries where there was no report, it was left black. And so there were more than 24 YouTube videos, more than 1,000 reports, and one of them I shared with you, which was played before this thing, and one of these have more than 500,000 hits. This have been compiled by my colleagues into 6 volumes. 2 volumes are in English language. This is in Asian languages. 4th volume is in East European, and 5th volume is in West European languages. And then it has also become a popular topic for competitive exams, civil services, banks, IIMs, IIT entrance, etc., etc. So that has been compiled into another volume. So that was as far as all the publicity that happened about it, which was not a bad thing to happen, because many times people are asked this, we are asked this question, that why do we do all this? What are the benefits? So at least there is some practical possibility. So this is all fine. But this is 4 years old story. What happened after that? So you see, one of the things which we recognized is that nature doesn't do something only once. If it has done it once, it must have done multiple times. Only thing, we didn't discover it earlier. So, and also if it has happened now, it will also happen in future. But what will happen in future, we don't know. But certainly we can look at what happened in the past, because we have 20 years of archival data. So one of my younger colleagues has examined and found there are 80 such events that have happened in the past. So, but before talking about that, I want to take you back to this event. Okay. So you see, I have shown you that this is perfectly aligned, but that was part of the story, as I mentioned at that time. In reality, what happened was the muon burst was delayed. We have corrected for the propagation time from L1 to Earth. But even if you correct for that, the muon burst was delayed by 28 minutes relative to the time predicted by magnetic field measurement. So there was a delay, and we didn't quite understand. We mentioned in our paper also, we also didn't pay attention. And then when my colleagues started analyzing the data, then he found that many such events show delays. So this is one event that happened on 22nd January 2005. Delay was 16 minutes. Red is, of course, always magnetic field. Blue is the muon intensity increase. Next event on 8th November, they are not in any chronological order. They are in the order of increasing delay. This was 20 minutes. Another event on 11th October 2001, 24 minutes. 4th November 2003 is a very fascinating event. In fact, instead of increase, it was a decrease because the magnetic field was oriented northward. As a result, Earth's magnetic shield became stronger, and we saw a decrease of 44 minutes. Decrease and delay was 44 minutes, 52 minutes, 64 minutes, and we have seen delays up to 2 hours. Now, we don't know why these delays are occurring. We have some clues. We are still looking at the data, but these 80 events are a gold mine for us. So what we are planning to do is to study the delay as a, can we correlate this delay with the properties of solar storm? If we can do that, maybe then we can build a model which can predict how much the delay will be. You see, satellites can never give you accurate prediction of what is going to happen because they tell you what happened at 1.5 million kilometers. What happened to solar storm after it arrived at Earth? What its interaction with Earth's magnetosphere does, nobody knows. The only instrument that can tell is an instrument such as Graves 3 sitting on Earth. However, if you detect it, then it's too late. It cannot give you warning. It can just tell you it has happened. But what can you do with it? Nothing. Unless you use it to arrive at a better understanding of what happens to solar storms. Why it is important? Because imagine, okay, what is the precaution you can take against solar storms? The only precaution you can take is, because you know air becomes conducting, is to shut down everything. Instead of lockdown, you have a global shutdown, okay? So you stop all electric supply, you shut down anything that has to do with propagation of electricity, and wait till the solar storm comes and passes and goes away, and the air, whatever ionization is through recombination gets neutralized, then you can turn back everything on. But imagine if the prediction was wrong and you shut down everything 2 hours in advance. And so world was without electricity for 2 hours. And then the storm comes 2 hours later and goes on for another 2 hours. So you have unnecessarily lost those 2 hours. Or worse still, if people said, well, maybe no storm is coming, switch back on, and then storm hits you after 2 hours, and then you are in trouble. So it is very important to have accurate prediction. I'm not saying that we have an accurate prediction, but there is a possibility that we can possibly, hopefully can understand this. At least it's worth a try because it has enormous societal implications. Okay, so I would now like to conclude by giving a brief summary. I hope I have convinced you that high precision measurements are vital for progress in science. Number two, it is important to carry out research where you have a natural advantage. You see, Ooty is an ideal location for such studies because it's close to geomagnetic equator. We are less susceptible to geomagnetic disturbances. We can look at northern and southern skies, both of them at the same time. If you are in up in the northern hemisphere or southern hemisphere, you can only see part of the sky. So in astrophysical research, that is a great advantage. And I hope I have convinced you that high energy particles are the best messengers and that the universe is the best laboratory. And these are not my statements. These are statements that I heard from some of the great scientists of 20th century. This first statement is due to Jim Cronin, who discovered CP violation. The second statement was told to me in a more colorful language by Robert Hofstadter, who discovered the structure of protons. And the third statement is by another great inventor by name Charpak. And the final sentence is actually by the founder of our laboratory, Professor B.V. Srikantan, who passed away last year. And this collage is a picture of members who contributed, both Indian and Japanese, to the success of Graves 3 experiment. I am just one of those participants, but most of the work is done by these people. And I'm thankful for your attention. Thank you very much. And I'll be very happy to answer questions if any.
Thank you, sir. I would like to request our coordinator, Dr. Vijay Kumar Singh, please If you have a question, please ask on behalf of his student.
Yes, sir. So, sir, there are several questions. So, out of them, first question from Chandan Raut, and he is asking, according to Dirac hole theory, we believe antiparticle have negative energy, but we know the black hole is composed of matter. Then how antiparticles are flies out towards center of the black holes?
Well, first of all, that is certainly not my area of research. You see, the negative energy state was, of course, a solution of Dirac equation, but in reality, in the quantum world, you know, a negative energy particle with negative charge is equivalent to a positive particle with positive energy, and so those are basically positrons. So as far as we are concerned, though they are antimatter, but for all practical purposes, as far as gravity is concerned, they play exactly the same role. So I don't quite understand the question, but the thing is that like we know that in nature we produce matter and antimatter all the time, and they show exactly identical gravitational properties, including those that form black holes.
Thank you, sir. Sir, there are another question by Vivek Kumar, and he is asking, with very weak interaction, can a quark transform into another quark of different flavor?
Okay, so you see, the thing is, you know, the quarks, for example, the heavier quarks can decay into lighter quarks. For example, you know, the two lightest quarks are U and D quarks, but the heavier quarks like charm or bottom quark or strange quark do decay into lighter quarks through weak interaction, and that is how they transform themselves. So finally, you end up getting either U and a combination of U and D quarks, and that is what we see: protons, neutrons, which are entirely made of up and down quarks.
Okay, thank you, sir.
Vijay,
So there
please
is
ask the question relevant to this talk.
yes, sir, yes, sir. So there is last question related to this one from Ronald Iskeria, and the question is there any explanation given to the change in the direction of difference in the magnetic field? The 1 with 3.8 sigma significance?
Can you please repeat? I could not hear the question fully.
Is there any explanation given to the change in the direction of the difference in magnetic field? The 1 with 3.8 sigma significance?
No, it is not 1.38 significance, 38 sigma significance. It is, see, whatever. Okay, so let me clarify two things. One is the actual direction of magnetic field in this calculation does not matter, because what we are trying to measure is not the absolute direction of magnetic field is not important, because what we are trying to measure is the change caused by magnetic field in the plasma. So it is a differential measurement. So we have Earth's magnetic field, so we get some result as you know, some number of cosmic rays reaching us, and then we superpose on that a varying magnetic field due to plasma, and that gives a slightly different field. Since we take the difference of these two measurements, the absolute value or direction of magnetic field does not matter. What matters is the magnetic field in space, which we know fairly precisely. I don't know whether it answers his question, but I don't think that the direction of magnetic field itself is relevant or important.
So there is one more question from Sonali Bhatnagar, and she is asking, do you have any solar models presently explaining the solar storm?
Well, that's a very good question, but very difficult to answer. You see, solar storms are basically a turbulent process, you know, and as we all know, turbulence is something which is very, very poorly understood. If it is a laminar flow or a streamlined process, it's easy to understand. But once you deal with fluids and deal with turbulent phenomena, they're extremely complex. So the only option that we have is to essentially depend on measurements. So we try to make measurements as best as we can. So the study of solar storm is basically an observational science. After you observe, then you try to make sense out of it. Let me give an example. For example, we know sun undergoes a 11-year cycle, right? Sunspots rise. It's not exact 11 years, but approximately 11 years. Nobody till now understands what is the origin of the 11-year cycle, even though it has been known for centuries. So we are dealing with a phenomena where we have very little understanding. So only thing that we can do, the best we can do is to study it as closely as we can, and especially because it can affect life on Earth. So that is why it's a very important topic. Okay.
So thank you so much, sir. We have finished all this question answer session. So now I request to Professor Venkatesh to proceed further.
Dear participant, we heard really very informative and motivational lecture with application that may save our life and planet Earth, of Dr. Sunil Gupta ji of Tata Institute of Fundamental Research and Cosmic Ray Laboratory, Ooty. I will request Dr. Vijay Raj ji, please give vote of thanks.
Thank you so much, sir. Today my words are not enough to express the gratitude, but still on the behalf of our physics department, I would like to thank our esteemed speaker, Professor Sunil Gupta, who graced us with his thought and giving us such an inspiring and motivational talk. I would also like to thank our beloved HOD, Professor Venkatesh Singh, for all words of wisdom that radiated a source of energy with us. We will ever remain grateful to you, and we thank you for being with us today. I also thank to all faculty member out of CUS who are from out of CUSB and also from CUSB. Particularly, I also thanks to Professor Brijesh Chaudhary and also Professor Prabhakar Singh who attended this talk. And from CUSB, I would like to thank Professor Budhendra Singh, Dr. Puneet Misra, Dr. Rohit Sahi, Dr. Nitin Chandra, Dr. Lakwinder Singh, and Dr. Akhilanand Singh, who always stand with us, guide us, leads us, and motivates us. We feel proud and thank you for making us feel happy and with your presence with this event. I also thank two wonderful students who have turned up in such a great number, not only from CUSB, but also from other institute. Last but not the least, I thank all the students for showing their interest in this science lecture series. Once again, thank you so much who have attended this seminar. Thank you very much.
So, dear participants and colleagues, that is all for now. We will see you next week, same day, that is on August 7 at our usual time, that is 11 a.m. with another wonderful speaker, Dr. Santosh Joshi of ARIS, Aryabhatta Research Institute of Observational Science, Manora Peak, Nainital. He will speak on telescope and its fabrication. Until then, stay safe, stay healthy, and keep thinking. Goodbye. Thank you, sir. Namaste, sir.
Bye. Thank you, sir.